Okay, so my name's Oliver Teall. I work for Costain, and I'm presenting this webinar on self-healing concrete. The tagline for this presentation is biomimetic multi-scale damage immunity, but don't worry too much about that because I'm going to explain all that in a bit. To begin with, as an introduction, Costain are one of the UK's leading engineering solutions providers with projects across natural resources and infrastructure. And they are the lead industrial sponsors for the research program which I'm currently involved in. And the research program is led by Cardiff University, and it's a joint venture with Cambridge and Bath universities. And it's funded by the Engineering and Physical Sciences Research Council. The program itself is a 3-year program known as Materials for Life, and it focuses around the creation of high durability smart materials. So to begin with, what I'm going to talk about today is first of all why this program exists, so the vision that created the drivers for the program. I'll go on to talk about the project partners, so who's involved, and the support that we've got from both industry and academia so far. I'll then go into an overview of the technical aspects of the program without going into too much detail. So what I'm going to do is give it, first of all, a high-level look, and then go into each work package individually, just 2 slides on each to give a brief summary of what is involved, and then on to what we expect from Materials for Life program and beyond, so what we're looking to achieve from the end of this program. So to start with, the vision was to create a sustainable and resilient built environment and infrastructure through the development of self-healing materials and structures that continually monitor, regulate, and adapt and repair themselves. And this is beginning with concrete, as concrete is the most widely used construction material in the world. And the aim of this was to then enhance the durability of our structures, thereby improving safety and reducing maintenance costs. And a big part of this was the fact that these materials should be inspired by nature. And again, that's something I'll come back to later on. So on the right-hand side of this slide, you can see the drivers, the key drivers which began the program off. So these are focused around the 3 aspects of sustainability. So social, environmental, and structural and economic. So from a social point of view, around 10% of UK traffic congestion is estimated to be attributed to roadworks. So by increasing the durability of our structures, we're reducing the requirement for repairing these structures. And for instance, on our road network or even our rail network, this reduces your congestion because you're reducing the amount of time you need to be on the roads and restricting traffic flows. From an environmental point of view, around 7% of global CO2 emissions are attributed to cement production. So again, by increasing the durability of our structures, we're reducing the amount of concrete we're using over the entire life of the structure to repair it and maintain it, thereby reducing the amount of cement we're using. And from an economic point of view, around £45 billion per year is spent on the repair and maintenance of existing assets within the UK. This is one of the biggest drivers. So the idea is to reduce your whole life costs by increasing the durability of your structures, reducing the requirements for maintenance and repair. And the aim coming out of these drivers is, as I said, to create a new generation of unique, versatile, and robust self-healing construction materials. And these will need to address structural or geotechnical applications and damage scenarios. And there's a focus on concrete to begin with, as I said, as the most widely used material. And the materials are inspired by nature, inspired by the idea that when you cut yourself, you heal yourself naturally. You don't have to have anyone, or normally, for small damage, you don't have to require external intervention to heal. And it's a self-healing system that works over multiple spatial and temporal scales. But again, I'll get on to exactly how it works a bit later on in the presentation. So to begin with, we need to understand the causes of the damage that we're trying to prevent. And this is just a summary slide of the sort of types of damage you see on concrete structures very commonly. And these are the sorts of damage scenarios that we're looking at healing using this new system. The program, as I said, is led by Cardiff University, and with Professor Bob Lark at Cardiff University side. He has underneath him are a number of senior research associates and lecturers, and as well as a number of PhD students. And the same can be said for Cambridge and Bath University. So in my role, I'm a PhD student at Cardiff University on their side of the research, as well as being the link with Costain. And the Materials for Life team in general includes, it's very interdisciplinary. It includes structural, geotechnical engineers, material scientists, bioengineers, bioscientists, and chemists. And when I get onto what each of the universities are focusing on, that will become quite obvious why that's the case. So I mentioned that we've got some interest from industry and academia, and this has really been quite encouraging. So from an industrial side, the Costain are the main industrial sponsors and responsible for providing site trials for the materials. There's also a number of other contracting engineers, consulting engineers, client organizations, R&D institutions, etc., who have all given their support to the scheme at bid stage. I'm not going to go through all the list, but there's a number of names there which are quite important in the construction sector within the UK. And within academia as well, there's a number of other universities who are also focusing on self-healing materials research, not necessarily self-healing concrete, but the techniques that they're using could be useful to what we're doing, and we are collaborating with these institutions. So for instance, at the University of Illinois, they're looking at self-healing polymers. University of Delft and Ghent, they've done a lot of work on the bacterial healing of concrete, which University of Bath are leading on from. And these are all being made aware of what we are doing and collaborating with us. Sorry. So to begin with, I just need to make a note about definitions of materials, because people mention smart materials or intelligent materials, and it sometimes gets confused what is meant by that. So on one side of the scale of your intelligence of material, you have what is known as intelligent materials, and this is what we're looking to eventually imitate. So these are things such as skin and bone, which can repair themselves over time, and they can monitor their own adaptations to their environment. So they can not only detect a change in their environment, but they can repair themselves and then regulate that change. On the other side of the scale, just above basic structures, you have what's known as sensory structures, and these are structures which can detect a change in their environment, but they cannot adapt to it themselves. They can only indicate that there has been a change, and they require external intervention. So an example of this is smart bricks, which can be used for structural health monitoring. In between these two is what's known as smart materials, and these are materials which can detect a change in their environment and then adapt to it, but they cannot regulate their own adaptations. So an example of this is shape memory polymers, and what these do is when there's a change in temperature, they change shape, but this is just a natural response due to their microstructure and processing, and it's not something they can then regulate. So in between these two is what's known as smart structures, and this is where we see self-healing materials falling in. What smart structures are is a combination of basic and or smart materials to exhibit structures which have smart behaviors. And by smart behaviors I mean ones that, again, like smart materials, they can detect a change and then adapt to that change. We're not at the stage yet where we can say they can fully regulate their own adaptations. So within that, self-healing concrete could be split into two main areas, which is natural healing and engineered healing. Natural healing processes in concrete are quite well known. This is when you crack a concrete beam, for instance, and then you leave it in water to cure, and it will eventually start to heal that crack. And this is due to several processes, such as the precipitation of calcium carbonate on the crack faces, and also the continued hydration of cement particles. However, this has severe limitations. It only works for very small crack widths, and it's quite a slow process. What we're looking at doing is moving towards the engineered healing, which is when you add extra materials into the concrete or using other techniques to heal larger cracks quicker and make it a more durable structure. And this is known as autonomic or engineered healing. So getting on to what this system we are looking at is, I mentioned earlier it was multiscale healing. What that really means is just it works at a number of different scales. So on the left-hand side of this slide, you see the scales that are being considered within the research, from very small nanoscale up to a macro scale, which is visible cracking. The concept behind this is that macro scale or visible cracks they don't just appear as they are, they develop over time from micro cracks which form due to those damage scenarios I mentioned earlier, until they become large enough to cause a problem. So they allow the ingress of water, salts, chlorides, etc. into the concrete matrix, which then causes a problem. It causes damage, and this is when you require repair to your structures, when you have spalling of your concrete, and you have corrosion of your reinforcement, etc. So the idea behind the self-healing system that we're looking at is to prevent the growth of these cracks and actually heal them at small scales. To do that, each of these scales has been split into work packages which is assigned to an institution, and they're then looking at techniques which work at that scale. So on the right hand side you can see the institutions which are involved, and University of Cambridge are looking at the nano and micro scale, and they're looking at using healing through microcapsules, and I'll get onto what this means. This is just the overview of what they're looking at. So they're looking at the smaller scale using microcapsules. University of Bath are looking at the micro-meso scale using microbial or bacterial action to heal slightly larger cracks. And what we're looking at Cardiff University in work package 3 is then a crack prevention system using shape memory polymers to restrict crack growth and to close an early stage cracking. Work package 4, then also led by Cardiff University, is to combine these systems into one multi-scale healing system, and also to look at vascular flow networks as an extension of the idea of a material which is inspired by nature. So again, I'm going to go through each of these individually now, just to give you an idea of what I mean by each of the techniques. So first of all, what University of Cambridge are looking at is microcapsules. On the top of this slide you can see the early stage images of the microcapsules. These are very small polymer or synthetic capsules which can contain a number of different cargoes which are healing agents. They can be used to heal the cracks in concrete. So the idea is to create these capsules and then mix them into the concrete, and then when cracking occurs, the crack either forms through the microcapsule itself, or there is a release mechanism for the capsule, for the healing agent, which then releases and glues the crack faces back together essentially. So this is just a number of the considerations they're having to look at when creating these capsules. So they have to have long shelf life, they have to be highly uniform, they need to be looking at the healing efficiency, the geometry, etc. So what they're doing at the moment is their current work. They're looking at different core materials, mixing conditions, wall forming monomers, etc., putting them through a polymerization process, and then they are investigating the optimum types of cargo and encapsulation materials to then put into concrete to allow for this healing mechanism. And again, this works at very small scales because these are only sort of 10 to 50 microns across, so they're quite small capsules. So to complement that, what the University of Bath are doing is looking at a bacterial action or a microbial action healing mechanism. So they're using alkalophilic bacteria which can survive in a highly alkaline environment for a long period of time, up to over 50 years. And this is exactly what we find in concrete. So they're introducing these bacteria. The aim is to introduce these bacteria into concrete along with a precursor and nutrients, and these can then lie dormant within the concrete matrix until cracking occurs, at which point, from a bacterial point of view, the environment becomes more desirable. And due to this, these spores then begin to germinate, and they feed off the nutrients and act as a catalyst for the production of calcite within the concrete, which then fills in cracks at a slightly larger scale from the microcapsules being developed by Cambridge University. So by combining these systems, we then have two different systems which can work to heal cracks of different sizes. So to give you an idea of what this looks like, on the top of this slide, the top two pictures are the natural healing process, which I was talking about earlier. So the white material around the crack on the top right picture is the precipitation of calcium carbonate I was mentioning. On the bottom is a specimen which has had bacteria introduced to it for the same healing process, and you can see that on the bottom right the crack has completely disappeared because it's been completely healed using this bacterial action. This is work that was done at Delft University. I mentioned they were also Bath were leading on from what they were doing, and the point of this is to show that the limitations of natural healing can be overcome by introducing bacteria into the specimen. However, this still has its own limitations. So this works over a period of time, and it has a limitation to the size of the crack that it can heal. So the idea is to then combine this with the other systems to create a much more resilient self-healing system. So as part of that, what we're doing at Cardiff University, and the research I'm personally involved in, is a crack prevention system using shape memory polymers. And shape memory polymers are being widely used within the medical, biomedical industry, also aerospace, but not so much within construction. And what they are polymers which are processed in a way to give them these shape memory properties. So they're essentially drawn at higher temperatures, around 80 degrees. Well, can be any temperatures. What we're looking at is around 80 degrees, and then cooled in a restrained position, which then locks in this temporary shape. When they're then reheated, they retract back to their original shape. And if we can anchor these within a concrete element, we can take advantage of this shrinkage force to then close cracks in concrete and also inflict a compressive stress upon the concrete, which restricts further crack growth. So the idea behind this is to use these shape memory polymers in whichever form we find most optimal, and then put them within a concrete beam to create a 3D pre-stress on the concrete beam. And preliminary investigations for this were very promising. So if we go on to the next slide now, we have been able to use these systems to close early stage cracks in concrete. Cracks that were first of all created using a 3-point bending test, and then the polymers were activated within the concrete to then close cracks. So we've proven this system works from a conceptual point of view and also from a small sample point of view. What we're doing now is upscaling that and looking at different forms of the polymer, whether it be strips, whether it be bars, whether it be strands, and looking at the best way of implementing it. So the idea is then to combine this to allow a system which actually restricts the crack growth to the sizes which the other two mechanisms from Bath and Cambridge can actually heal the cracks, thereby significantly increasing the durability of your concrete structure. So as I mentioned, the next stage of this, at the moment each of the institutions, Cambridge, Cardiff and Bath, are looking at the techniques in an isolated perspective. So once the first stage of this is complete, which is due to be complete in September, we'll then be looking to combine these into one system to then see how best to combine the systems to create a high durability self-healing system, and then put this onto site trials. And the timescale for site trials we're looking to begin these in summer 2015. So as Costain are the main industrial sponsors, and as I am the Costain representative within Cardiff, it's my responsibility to identify potential site applications and look at implementing these site trials. And this will initially most likely be within a non-critical or temporary works application due to the pilot nature of the scheme. What we're looking to do is combine this with monitoring techniques to prove that our system has high durability and it works in a site environment, and to further the investigation into self-healing materials. So I also mentioned there is a focus on extending that idea of inspired by nature, and this is through the flow networks, which is also part of Work Package 4, which Cardiff University are running. So the idea that the human body has veins and capillaries running through it, in the same way you can engineer a concrete element to have flow networks within it, which you can pump a healing agent through to then heal cracks as they occur, but this is then a system that can be reused again and again. So this came initially from experiments using capillary tubes containing healing agents, which were cracked, and then the healing agent leaked out and healed the crack. However, this is obviously a finite system, so once it's cracked, it can't be reused. So the extension of this was to create a flow network within the concrete where healing agents can be pumped in as and when, and all you need to do is monitor the concrete element, and then whenever damage occurred, then go and pump these healing agents in, which is a very easy form of repair, essentially. So this is a sort of an addendum to the rest of the research program, and it's something that we're hoping can then augment the other systems. So we've also received quite a lot of attention outside of the UK. For instance, in the FIATech SETI Awards 2013, we won the category of Intelligent Self-Maintaining and Repairing Operational Facility. And all the CIRIA Tech Awards are to do with implementing innovations and mainly technological and engineering innovations within construction. And we had a very promising response from them, and in the form of the award, of course, and that really helped to boost our publicity of what we're doing. It was also voted the research most likely to change the world in the British Science Festival 2013. So again, very good recognition and a real indication that this has got some real potential, as well as the interest we've already had from both academia and industry. So what are we looking to do beyond this? Well, the focus now is, of course, the research program and then the site trials to then summarize the research to date. And it's all part of this development and demonstration of a suite of self-healing construction materials. So this is the start of what we're hoping will be many future projects. The establishment of a UK Virtual Centre of Excellence to then act as a platform for all of these different institutions who are developing self-healing materials. So this is one of the most advanced self-healing materials research programs there are out there. And it's certainly unique, as in there are no other research programs which combine techniques in the same way that we are doing now. And so we're looking to then bring together that relevant international community for the first time to make significant advantages. The establishment of site-based demonstration projects is obviously key to then prove that this is a system that can be used in construction, and the continuation of this work following these trials, because of course they won't be the end of it, through additional PhD projects and with others, and then also the acquisition of additional funding following the initial 3-year period, and to further exploit the momentum of Materials for Life. So this all comes down to the aim, or the 3 key drivers mentioned at the start, and the idea that this is part of a wider agenda of creating the infrastructure of the future, and in combining our current infrastructure with intelligence to then create adaptable, self-sensing and self-repairing structures which can aim in those 3 key drivers. So that's pretty much everything. Any further information there, we do have a website which is updated as and when, and hopefully that can give an insight into what we're doing, and any more questions I would be happy to answer. Thank you.